let's investigate this function and see if we can think about what it means to evaluate its limit. So the function we want to look at is up in that top left-hand corner there. We've got the function x cubed plus x squared minus 17x plus 15 over x minus 1. And we can see from the graph of this function that we get this nice parabola. And because of the x minus 1 in the denominator, at x equals 1, there's a hole in the function. Right, so we can see from the graph that it's a hole. We know that that's just going to be a place where the function is undefined. So maybe it would be a hole, maybe it would be an asymptote. And using limits, we can actually determine what that would be. So we can see that when we take the limit, and we're sort of used to this idea, looking at limits from a graph from Calc 1, the limit just tells you where the function is approaching when x is getting close to negative 1. Right, so as positive 1. As x is getting close to positive 1 here, that dashed gray line is x equals positive 1, the function is getting closer and closer to negative 12, even though it doesn't ever quite touch negative 12. So let's look at that in terms of a table of values for the function to kind of see what that means. So I've got my table over here on the left, and we can see as x is getting closer and closer to 1, those function values are increasing towards negative 12, and then they're going to go a little bit past negative 12 on the other side of 1. So how close to negative 12 do I get? So can I get within 1/10 of negative 12? So as long as I have 0.98 or higher up to 1, or 1.02 on the other side, right, in that range, then I'm going to be within 0.1 of 12. Can I be within 0.01 of 12? Can I be within 1/millionth of 12, right? How close can I get to negative 12? I keep saying 12, but I mean negative 12. So let's go ahead and look at that graphically. So I want to think about being really close to negative 12 here. So I can draw in sort of a dotted line around negative 12, and that's just going to be some distance from negative 12. That distance is represented by the Greek letter epsilon. So I want to say, okay, can I be within here, my epsilon, let's make it just 0.1 to start with. Can I get my function to be within 0.1 of 12, negative 12? So it's going to be from negative 12.1 to negative 11.9. And right, if I zoom out really far, I can see there's going to be two different places when I'm going to get next to negative 12. But the one I care about is when x is close to 1. So how close to 1 does x need to be so that the function values are within 0.1 of negative 12? That's the question we want to ask. So we want to think about some little region here around x equals 1. And I want to think about how much of a region can I have. So maybe I can make this a little bit bigger. So within that red area, the function values are still going to be within 0.1 of negative 12. So I can get that to be within 0.1 of negative 12. Can I get it to be within 0.01 of negative 12? Again, I'm going to zoom in here. Now that same distance away from x, that's called my delta. That's not going to work, right? If I'm looking at that red region, in that red region, the function values aren't always stuck in the blue region. But if I make that a little bit smaller, let's say I make it 0.03, now we can see in that red region, is the function value always going to be in the blue region? Not quite, but I can make it a little smaller still. And now in that red region, I can make my function values even that much closer to negative 12. So what we want to do is for every distance away from negative 12, we call that distance our epsilon. So for every epsilon greater than 0, when I can get my function to be that close to negative 12 by making my x value really close to 1, but not necessarily equal to 1. So that's this idea that we want to be able to use and make precise. So for every epsilon greater than 0, we can get the function value to be within epsilon of negative 12 by taking x to be within some delta of 1. So let's go ahead and write that out. So we have, for every epsilon greater than 0, we want to get our function close to negative 12 by making x within some delta to 1. So again, let's go from this idea that we talked about and see if we can change it into symbols. So we're pretty close. We've got for every epsilon greater than 0, we can get the function close to negative 12. So that means that the distance from my function to negative 12 is small. So the distance from the function to negative 12, that gives me the distance. And I want it to be close. I want it to be epsilon close, right, within that epsilon that we picked. So that's going to be epsilon when x is within some delta, right? So there existed some delta that was also greater than 0. That when the distance from x to delta, when the distance from x to 1 was less than delta, we got the distance from f of x to negative 12 to be less than epsilon. So that is our precise definition. We'll go ahead and write this in general on the next slide and then talk about it one more time. So again, our precise definition of limit in general now is if we have a function f from x to r, where x is a subset of the real numbers and c is of some real number, then the limit as x goes to c of f of x is equal to L if for every epsilon greater than 0, there exists some delta greater than 0, such that the distance from f of x to L is less than epsilon whenever the distance from x to c is less than delta. And I add one extra little piece here. That distance between x and c has to be strictly greater than 0. X can't equal c here because the function might not be defined at c. So remember, this whenever is just kind of another way of writing like an if-then, but it's kind of backwards. So another way to think about it is for every epsilon greater than 0, there exists a delta greater than 0, such that when x minus c is between 0 and delta, so the distance from x to c is less than delta but bigger than 0, that means that f of x minus L, that distance between f of x and L, is less than epsilon. And one thing to remember is that when we have these if-thens, it's based on this x, so we have this implied for all x in there. So that'll be helpful when we're going to negate this definition. Okay, so what does it mean? For every epsilon greater than 0, that epsilon comes into a play with the distance between f of x and L. So I'm going to think of this epsilon over here. For every epsilon greater than 0, we can get the function to be within epsilon of L. So this is a distance of epsilon away from L that I've drawn here. I can get that function to be within epsilon of L as long as x is close enough but not necessarily equal to c. So how close do I need to go to c? It looks like as long as I'm in this region here, then my function will be in that epsilon band. So I could let that be my delta. I could also let anything smaller than that be my delta. But in particular, I don't have that x equals c because I'm allowed to have the function have a different value at c. It doesn't have to be the value at that point, and that limit will still exist. So for given this epsilon, given this distance away from my L, I was able to find this delta distance so that for every x within this range here, for every single one of these x's, the function value is between f of x. The function value is a distance of epsilon from L. So this function value is between L plus epsilon and L minus epsilon. Okay, so let's use the precise definition of a limit to prove that the limit as x goes to 2 of 3x plus 4 is equal to 10. So we need to show that for every epsilon greater than 0, there exists some delta greater than 0, such that for all x, we get that 0 less than absolute value of x minus 2 less than delta implies f of x minus 10, that distance, is less than epsilon. That's what I want to try to show. So we're going to sort of split our page up into two here. We'll have our proof, but then we also are going to need some background work, because let's think about how we actually need to do this proof. So because the first part is a for all, I'm going to let epsilon be some fixed but arbitrary real number greater than 0. And now I need to show what epsilon should be, right? We need to show there exists an epsilon, so I can give a formula for epsilon, and it's allowed to depend. Sorry, I need to show a delta exists, so I can give a formula for delta, but it needs to depend on that epsilon, or can depend on that epsilon. So let's think about what I want to try to show. So I want to try to show, in my last thing, that f of x, which is 3x plus 4 minus 10, I want to show that that is less than some epsilon. So I haven't shown it yet, but because I'm just doing my scratch work, I'm allowed to write that down. Right, that's what I want to show. So that's the same as showing that 3x minus 6 is less than some epsilon. So then I can factor out that 3 that they have in common, and that's the same as showing 3 times the absolute value of x minus 2 is less than epsilon. And now we notice we can get this x minus 2 to be smaller than whatever we want. So I can say that as long as that x minus 2 was less than epsilon over 3, then I should be in good shape. So I can just let this be my delta. So let's see what happens when we do that. We'll say we can, I think let's use let again, let delta equal epsilon over 3. And now I'm trying to prove this if-then, so I'm allowed to assume my if. So I can assume that x minus 2 is less than epsilon over 3. Then I'm trying to prove that f of x is less than epsilon, or f of x minus 10 is less than epsilon. So let's see if we can do out that algebra. So then I get that x minus 2 is less than epsilon over 3. So we're basically going to follow all of our steps in the background work backwards. 3x minus 2 is less than epsilon. 3x minus 6 is less than epsilon. 3x plus 4 minus 10 is less than epsilon. So my f of x minus 10 is less than epsilon as needed. So we were able to show, given some epsilon, how to find the delta to get f of x minus 10 to be less than epsilon whenever x minus 2 was less than that delta. So that's our proof. I encourage you to go back, read over this, see why we did each of these steps, where they all came from, and how you could do this for a different proof. Okay, for this question that I want you guys to work on, I want you to consider the limit as x goes to 3 of 2x plus 1. We know that that's going to equal 7. And we're going to sort of build up a proof. So first I want you to let epsilon equal 0.5 or 0.5 and figure out which delta is going to give you that when x minus 3 was within delta, or x is within delta of 3, that 2x plus 1 is going to be within epsilon of 7. So I forgot to put the 7 in here. Let's add that in. So I want that 2x plus 1 minus 7 to be less than epsilon. So find that delta when epsilon equals 0.5. Then find the same delta. So same question, but now epsilon equals 0.05. And then for general epsilon, what would that delta be? And once you do that, then you can go ahead and write out the nice precise proof that this limit does equal 7. Okay, so let's do one more example. We want to prove that the limit as x goes to 2 of 5x squared equals 20. So again, that means we want to show for every epsilon greater than 0, there exists some delta, such that for all x, as long as x minus 2 is less than delta, bigger than 0, we get that f of x, which is my 5x squared, minus L, which is 20, is less than epsilon. So here, again, we want to let epsilon be greater than 0, and then we need to give a formula for what delta should be. So we're going to need to do some background work to figure out what that delta should be. So I know that I want my 5x squared minus 20 to be less than epsilon. And I can get that to be true by letting x minus 2 be less than something. So I want to think about how I can kind of algebra this, do some algebraic manipulations until I get it to look like an x minus 2. So I notice there's a common factor of 5, so let's go ahead and just pull that outside of the absolute value because it's a positive quantity. And I get 5 times the absolute value of x squared minus 4 has to be less than epsilon. And then I can factor that into x minus 2, x plus 2. And now, right, we could do this thing where I just solve for this x minus 2 inequality. I get epsilon over 5 times the absolute value of x plus 2. But you're not allowed to say what epsilon is in terms of x. So I'm not allowed to I'm not allowed to say what delta is in terms of x. So this can't be my delta since it has some x in it. So we need to keep working, and we need to think about, is there something that I know that this quantity is definitely going to be less than? So I can find, if I had some delta here, and I knew x was less than that delta, then I wouldn't necessarily know that it's going to be less than this. So I actually want to find some quantity on the other side, right? If I make some quantity in between here, my delta, then if I have x minus 2, and I know it's less than some delta, and that delta is less than epsilon over 5 times the absolute value of x plus 2, then for sure x is going to be less than that. So I'll be good. So I want my delta here to be less than epsilon over 5 times x plus 2. But how do I make it less than? I need to make either the numerator smaller or the denominator bigger. So if I make the denominator bigger, if there's some number I know that's bigger than the absolute value of x plus 2. Right, so there's definitely kind of some logic we have to do here. Well, let's think, what do we know about this x plus 2? Give ourselves a bit more space here. So x plus 2 absolute value, we should think about as the distance from our x to negative 2. But I know that x is really close to 2. Maybe it's bigger than 2, maybe it's less than 2. And I'm trying to figure out how big this distance is. And I want to find something that it's definitely going to be less than. So how big can that distance possibly be? Well, I know that x has to be within some delta on either side of 2. So by restricting how big my delta can be, we can make sure that that x plus 2 distance can't be too big. So let's say that delta is at biggest 1. So the biggest distance we can have is 1. So the furthest away my x could be is if x was way over here at 3, in which case that distance would be 5. So let's see that algebraically. I'm just going to do that up in the corner here. So we'll kind of give ourselves some space. So what do I know? I know that my x minus 2 is in absolute value less than delta, which means that x minus 2 is between negative delta and delta. And what I'm saying here is that my delta is going to be at most 1. So then negative 1 is less than negative delta, which is less than x minus 2, and that delta is less than 1. Sorry, I put a greater than or equal to here. I meant to have a less than or equal to. All right. Now, that's what x minus 2 is going to be. let's think about what x plus 2 is. So I'm just going to think about these three pieces of my inequality. So I get x, let's add 4, so I get x plus 2. So x plus 2 is between 5 and negative 3, right? Which makes sense. If it was as close as possible, that would give me 3, not negative 3, but positive 3. If it's on the other side, I get 5. So x plus 2 has to be between 3 and 5, which means that absolute value of x plus 2 is certainly less than 5. So now I know that we can let delta equal epsilon over 5 times the 5 from that x plus 2, and that's going to be less than epsilon over 5 times x plus 2. All right, so let's see if we can put this all together. So we're going to let delta be epsilon over 25 here. And now I'm going to assume my if. So assume that 0 is less than x minus 2 is less than delta. Sorry, epsilon. Yeah, delta, which is going to equal epsilon over 25. And I want to show that 5x squared minus 20 is less than epsilon. So we can note that, oh, wait, we need to include one more thing here. We need to make sure it's actually going to be less than 1. So I'll have it be the minimum of that and 1. So whichever of those is smaller. So it is going to be less than this. And we get that x minus 2 in absolute value is less than 1, because it's delta is the smaller of those. So it's less than or equal to that, and it's also going to be less than 1. So we get, going back through that same process we did before, if I add 4 to everybody, I get that x plus 2 is between 5 and 3. So absolute value of that is less than 5. We need to use that, so I'll have it ready to go. So x minus 2, which is less than epsilon over 5 times 5, is less than epsilon over 5 times x plus 2. I'm making the denominator smaller here, so I'm making the whole thing bigger. Then, multiplying across, we get 5 times the absolute value of x minus 2 times the absolute value of x plus 2 is less than epsilon. So 5x squared minus 20 is less than epsilon, which is what we wanted to show. So with this square here, it was definitely harder algebraically. There was lots of different things we need to do. This is the type of proof you'll do often in a course like analysis, but it's good to practice now. So you'll see a lot more of these in Math 3150.